Welcome to part 4 of our Fundamentals of Spectroscopy series. My name is Shane Harrell and I'm going to talk about optical spectroscopy at the extremes. I came up with a few questions that I think push the limits of what can be done with optical spectroscopy. The first one is, can we design an experiment that can measure processes that involve the emission of just a single photon? To do so, you'd imagine that you'd need an experiment that is extremely sensitive to light. The second question is, can we measure things in physics and chemistry that happen really, really fast? 1 billionth, 1 trillionth, or even 1 quadrillionth of a second. Here, you need a setup that has very good time resolution. And the last one is, can we use spectroscopy to provide high-density, highly informative chemical or elemental maps of a sample? This would tell us not only what our sample is made of, but also tell us about the spatial distribution of the different elements or chemicals in the sample. This would be a lot of data, and it could take thousands of spectra to make one of these maps. So you would need an experiment that had high throughput to collect all of this data in a reasonable amount of time. Here I'm showing again one of our generic spectroscopy setups. It's made of some sort of light source, which could be a laser, a broadband source, it could be X-rays. That light goes ahead and interacts with the sample. The light is collected and dispersed into a spectrometer and then detected with some sort of photosensitive device. Now, in sessions 1 and 2, we talked about the different things that can happen when light and matter interact, like transmission, reflection, absorption, the emission of photons, and some of the different spectroscopies you can do with these light and matter interactions. In session 3, Adam talked a lot about spectrometers and how they're used to disperse light. This talk is going to focus a lot on detectors and how detectors can be used to overcome some of the challenges in spectroscopy that we're talking about. Let's take a minute to talk about how to detect photons, and it's based on the photoelectric effect. You can take a semiconductor, and in the semiconductor there are two main energy levels for the electrons, the lower energy valence band, where the electrons are not conductive, and the higher energy conduction band, where the electrons are conductive. And these levels are separated in energy by an amount called the band gap, and here I'm showing silicon, and the band gap for silicon is 1.14 eV, or about 1088 nanometers if you go ahead and convert to wavelength. What can happen is when light comes in, and this light has to have energy greater than the band gap of the material and interacts with the material, it can take electrons from the valence band and excite them into the conduction band. And if you go ahead and put an electric field on this material, you can move these electrons in the valence band and generate a current. And this is the basis for our signal, the photocurrent. Now, silicon isn't the only material you can do this with. You can do it with other materials too, like indium gallium arsenide or InGaAs, which has a different band gap than silicon. It's actually lower. So InGaAs can be used as a photodetector for the shortwave infrared, while the band gap of silicon is optimized for detecting photons in the UV visible and near IR. In the last session, Adam talked a little bit about array detectors, where array detectors are a collection of photosensitive pixels that are integrated together to make a 2D sensor or a camera. These are called CCDs, or charge coupled devices, and they come in a few variants: EMCCDs, ICCDs, complementary metal oxide semiconductor, CMOS, or even ICMOS. Over here I'm showing a CCD where you have a collection of photosensitive pixels in light green, and down on the bottom in dark green you have the readout register. What happens in a CCD is when light strikes a pixel, it can generate an electron in the pixel by the photoelectric effect, like we just talked about. Then a voltage is used to take the electron from the pixel and bring it down to the readout register, where the electron is converted into from a charge into a voltage, and this is what generates our signal. Now we'll focus on optimizing detector sensitivity, and we'll see some examples of how detector sensitivity can be used to do spectroscopy at the single photon level. When we talk about sensitivity in a spectroscopy experiment, we're really talking about the signal-to-noise ratio of the measurement, and this is what we want to maximize. Here we're looking at a signal generated from a photodetector and showing the different things that contribute to the overall signal-to-noise ratio. The first thing to look at is the average signal intensity, and that's just how big the signal is. And that depends on a couple of things. It depends on how many photons are reaching the detector, and it also depends on how efficient the detector is at converting a photon into an electron. But we've already talked about how we'd like to be able to measure processes that emit single photons, so we can't control the photon level, but we might be able to do something about how well the detector turns a photon into an electron, and that's all about the quantum efficiency, which we'll talk about in a bit. We'll also look closely at a couple of noise sources, the read noise and the dark noise, and we'll talk about ways to minimize their contribution. The overall signal-to-noise ratio is calculated by this equation up here, where you have the signal intensity divided by all the different noise contributions summed in quadrature. So it'd be good to make this numerator as big as possible and make this denominator as small as possible. There are mainly two ways to control or tune the quantum efficiency of a detector, and that's with the sensor architecture or design, or the way you pick and integrate all the components around the sensor like windows, electronics. And then there's ways to treat the sensor material itself. On the left, here are some quantum efficiency curves for different types of detectors and detector designs. You can see that back illuminated CCDs and SCMOS designs can get quantum efficiencies well over 50%. You can also have front illuminated CCDs, intensified CCDs, and they all have their own quantum efficiency curves. On the right here, I'm showing the effect of quantum efficiency from different treatments on a sensor, such as anti-reflection coatings can be applied to the silicon, bulk silicon can be etched away to expose more of the depleted region. That improves quantum efficiency. The quantum efficiency can be tuned a little bit towards the IR based on some of these treatments. So depending on what type of experiment you're doing, where in the spectrum you're working, and what type of quantum efficiency is needed, there are a number of detector options available. And just to remember, the quantum efficiency is the number of electrons that you get out of a detector divided by the number of photons that go into the detector. We saw earlier that one of the noise contributions to the signal-to-noise ratio in a measurement is the dark noise. So let's have a look at the dark noise and see if there's anything that can be done to reduce it. I'm showing over here again a picture of our silicon photodetector where there are electrons in the valence band, which can be excited by incident light, to the conduction band. An electric field can be applied and we can produce a photocurrent. Now, it turns out that there are electrons that have enough energy at a given temperature to actually be in the conduction band, and if an electric field is applied, they're going to go ahead and produce a current even though no light is incident on the sample, and that's called the dark current or the dark noise. Now, the number of electrons in the conduction band depends on a couple of things. It depends on the band gap of the material, so the higher the band gap of the material, the less number of electrons will be in the conduction band. And it also depends on temperature. And this temperature dependence can be understood by a Boltzmann-like distribution that I'm showing here, where I'm plotting a number of particles having a particular speed or energy as a function of temperature. So you can see that as the sample is hotter, there's a greater number of particles in the sample that have a higher speed or higher energy at a given temperature. So we do have a way to reduce the dark current because we know that the number of electrons in the conduction band depends on temperature, so the sensor can be cooled to reduce the dark current or reduce the dark noise. This slide shows the effect of temperature on the dark current. Here, I'm showing the dark current in number of electrons produced per pixel per second for a few of our sensor types as they're cooled down. And you can see that in most cases, there's a linear relationship between dark current and temperature down till about -80 or -90 degrees or so Celsius, and then it starts to flatten out. And while this graph has some good information, I think it's also good to see this effect through pictures. Here we have an exposure of a weak LED on the same sensor with the same exposure times, where the sensor is cooled down to two different temperatures, -70 degrees Celsius and -95 degrees Celsius. And you can see the additional cooling really cleans up this image, and that's because we're reducing the dark current at this lower temperature. Over here on the right is a dark image, also at two different temperatures, -30°C and -80°C. And you can see how the image where the sensor is cooled down to -80°C is actually darker, right? There's less speckle in the image, and that's also because the dark current has been reduced when you cool down to a lower temperature. If we take a horizontal slice of this image and plot the spectrum down here below, you can see that many features in the spectrum due to the dark current go away as the sensor is cooled down. We just saw how we can improve the signal-to-noise ratio, or the sensitivity of a measurement, by cooling the sensor to reduce the dark current, but are there any other ways to improve sensitivity? And the answer is yes, and one way to do it is with EMCCDs. Here we're showing a sensor where we have the active pixels up here and the readout registers down here on the bottom. Now we have our conventional ADC channel, but we also have an additional channel in this case, and this is called the EM channel. What can happen in the EM register is that the photoelectrons generated in the silicon can go ahead and be amplified in this EM gain register through impact ionization if gain is applied. So one photoelectron that's generated in the silicon can be amplified into many, many electrons by impact ionization in this gain register. And that's a way to take a very, very weak or small signal and make it bigger, amplify it. So the applications of EMCCDs, again, are to be able to detect very, very weak signals, such as single photon, like we're trying to do. And it's also a way to overcome readout noise at high readout rates. So the faster you read out one of these CCDs or sensors, the higher your readout noise is going to be. But you can reduce the effect of that readout noise by increasing EM gain, although there is a cost in dynamic range of the measurement, but we'll talk about that more later. This is a comparison of the signal-to-noise ratio, or sensitivity, of a measurement for a detector that's operating in conventional CCD mode and EM mode. The signal-to-noise ratio is plotted on the y-axis for a given set of parameters: exposure time, readout speed, cooling temperature, and incident photon wavelength. And on the x-axis, we're showing the number of photons per bent column. The signal-to-noise ratio for the conventional CCD mode is this trace in orange, and blue is the detector working in EM mode. You can see that when we get to about 77 photons, the signal-to-noise ratio is the same for both modes, and for any photon flux below this, the signal-to-noise ratio is higher in EM mode. So operating in EM mode is a good way to enhance the sensitivity of a measurement at low photon fluxes. This slide shows the effect of increasing EM gain on a weak signal. You can see over here on the left that we have a weak signal taken on an EMCCD, and as we increase the gain 1x all the way up to 500x, you can see how increasing the EM gain improves the image quality by bringing the noise floor down to a negligible level. On the right, we're taking a horizontal slice of this image and plotting a spectrum where we are increasing the EM gain from lowest gain down on the bottom to highest gain on the top. And you can see how the central spectral feature here, which isn't detectable at the low gain setting, cleans up quite nicely as we increase the EM gain, and along with that we get a reduction in the noise. This is another example of how increasing the EM gain can influence the signal-to-noise ratio in an experiment. Here we're taking a Raman spectrum of polystyrene, and we're focusing on the aromatic carbon band, which comes out at about 1,000 wave numbers. The left-hand plot shows how the exposure time can be reduced for this measurement by applying EM gain. So the green spectrum was obtained with applying EM gain, and the blue spectrum was taken in conventional mode. And you can see that you can reduce your exposure time by about a factor of 50 to get a spectrum with about the same signal-to-noise ratio as when it was taken without the EM gain. On the right, we have two spectrum with the same exposure time, but one with EM gain off, here in blue, and the other with EM gain applied, here in red. And you can see that the spectrum taken with the EM gain off, it's very difficult to make out any features unless you amplify or you blow out the spectrum by about a factor of 50. Now you can see this aromatic carbon mode at 1,000 wave numbers, but you'll also notice that this spectrum is much noisier than the spectrum taken when the EM gain was applied. And this is one last example where we can look at the effect of EM gain on sensitivity. These are biological cells stained with a couple of dyes that are commonly used in biological imaging: ODIPI on the top and Texas Red on the bottom. And for each case, we're taking images where no EM gain was applied, and then we turned on the EM gain. And it's very apparent here how the EM gain can improve the sensitivity of this measurement, where you can barely see the cell with no EM gain, but then you can see it really well when the EM gain is turned on. Now, one of the questions at the beginning of this presentation focused on the ability to measure processes in physics and chemistry that involve the emission of single photons. One example of this is single molecule spectroscopy, so I'm showing again the absorption and emission spectrum of fluorescein, which we talked about in session 2. You'll notice that both the absorption and the emission spectrum are relatively broad, and they cover a rather large wavelength range. One reason for that is we're taking a bulk measurement, and that means that we're getting absorption and emission from a large number of molecules in the sample. We also talked about in session 2 solid chromatic shifts and how absorption and emission wavelengths could be shifted based on the local environments that the molecules are exposed to. One way to think about the spectrum is that it's a collection of weighted averages of the absorption and emission spectrum of all the different molecules in the sample. So you might have some molecules that are absorbing down here at 440, but you might have another collection of molecules that are absorbing here at 480, and likewise some molecules are emitting at 520 while some are emitting at 560 nanometers, all based on what type of local environments they're exposed to. And this can be 10 to the 5 molecules or even higher. It makes the spectrum inherently broad. Now, this effect is also shown with this plot over here on the right, where we're looking at an absorption spectrum, a simulated absorption spectrum of 10,000 molecules all the way down to 10 molecules. And you'll notice a couple of things that are going on here. One is that the spectrum intensity, the signal intensity, is getting smaller. And also what you'll notice is that this broad feature that you see with 10,000 molecules in the sample starts to be broken down into more distinct, narrower, and discrete features as you reduce the number of molecules in the sample. So if we imagine that we could take a spectra of just a single molecule, the spectrum of a single molecule could be a very sensitive probe of the local environment that the molecule is exposed to. There are a few things to consider when doing single molecule spectroscopy. The first one is how to isolate the sample to make sure that you're collecting a spectrum from only a single molecule. And there are several ways to do this. Cryostats can be used to cool low pressure gases down to temperatures where single molecule spectroscopy can be done. But this can be expensive to set up, and a low pressure, low temperature gas may not be a representative environment for something, say, like a biological molecule. Another way to do this is to immobilize the sample, and this can be done by using a polymer matrix like PVA or PMMA, or you could use a functionalized surface and take advantage of the chemistry interactions between the sample and the functionalized surface to immobilize your target molecule onto the surface. The second thing to think about is that the optical setup should be sensitive to only a single molecule, so the active optical area, the place where the spectroscopy is going on, needs to be carefully localized. This usually involves some type of microscopy approach, and I'm showing a few ways to implement the microscopy approach over here. Finally, like we talked about, since we're looking at the spectrum of a single molecule, we need to get the best signal-to-noise ratio possible in order to see something. To do this, it'd be good to have a bright sample, and by that I mean a sample that either has a high absorption coefficient or a high fluorescence yield. It's also necessary to minimize the background photons and interference from molecules that you don't care about that might be in your sample. And it helps to have a highly sensitive detector, which means a highly sensitive camera that can measure weak signals, and a high throughput spectrometer, which can get as much light as possible to the detector or to the camera. Now we'll have a look at a couple of examples of single molecule spectroscopy experiments. This is a single molecule experiment of a dye called QDI. Now, QDI is a dye that falls into the class of Rilene dyes, which I'm showing here. And Rilene dyes are known to make use of these naphthalene rings that are linked together. And people like to use Rilene dyes in single molecule spectroscopy because they tend to be very bright and they tend to have high photostability. And this experiment took PDI and it put it into a PMMA polymer matrix. What you see here on the left is the emission spectrum of several individual QDI molecules in this polymer matrix as a function of position, and the excitation wavelength was ranged from, or varied from 570 nanometers to 750 nanometers. So what the color of these peaks correspond to is they correspond to the color that the sample needed or the molecule needed in order to make it fluoresce. So these molecules over here needed 570 nanometers to make them fluoresce. This molecule over here needed 750 nanometers to make it fluoresce. Over here on the right-hand side, these solid dark traces that are gray shaded correspond to the absorption spectrum and the emission spectrum or fluorescence spectrum of QDI in a PMMA toluene mixture, while the brown trace corresponds to the absorption spectrum of QDI in a PMMA polymer matrix. So the brown trace is QDI when it's in the solid polymer matrix, and these dark traces, gray shaded, are the spectrum of QDI in a liquid mixture. And you can see just by placing the QDI in a polymer matrix, it shifts the absorption spectrum. Box C is showing the fluorescence emission spectrum of a few different individual QDI molecules in the PMMA matrix. And again, the color corresponds to what light the molecule needed to make it fluoresce. And if we look at M1, that's this molecule right here, which absorbed at 680 nanometers and is emitting at about 700 nanometers. And M2, which absorbed at about 710 nanometers, is emitting at about 750 nanometers. And the bottom chart is just showing a histogram representing the emission maxima for all the molecules measured in the sample. So Y is the number of occurrences of how many times a molecule will emit at a given wavelength. And you can see that the emission spectra for the individual molecules have different wavelengths. And again, that's because they're subject to different local environments. This is another experiment where we're looking at the single molecule fluorescence of a dye called dye I. Now, dye I is another one of these dyes that's used a lot in biology for cell staining and imaging. Here again, the dye molecules are being immobilized by putting them into a PMMA polymer matrix. And the top left images here show the far-field fluorescence of these dyes in this PMMA film, showing the individual fluorescence of dye molecules here in figure A and down in figure D. Now, if we go ahead and look at the fluorescence emission spectrum of both of these molecules in figures B and E, we can see that the emission maximum for each of these molecules is different. And we can also look at the time-resolved fluorescence spectrum of these molecules in figures C and F, and we'll notice, we talked about this in the fluorescence lifetime in session 2, that the fluorescence lifetime for these molecules are different. And again, that's just indicating that these molecules are exposed to different local environments, and that's affecting their fluorescence emission spectrum and also their fluorescence lifetime. And that information isn't available if you take a look at the bulk emission spectrum in figure G, and also the bulk fluorescence, time-resolved fluorescence spectrum in figure H. I wanted to shift gears a bit and take a minute to talk about quantum entangled photons. Now, experiments with quantum entangled photons usually involve some sort of imaging and not so much spectroscopy, but it's a great example of how single photon sensitivity of detectors can be used. What are quantum entangled photons? Quantum entanglement is a phenomenon where two particles which interact with each other can remain connected, instantaneously sharing their physical states no matter how far apart they are. Quantum entangled photons show up in many areas like fundamental physics, quantum metrology, and cryptography, but I'm going to show an example about how they can be used for enhanced imaging. Before we see how quantum entangled photons can be used for enhanced imaging, let's take a look at classical holographic imaging. To create a hologram, you can take a coherent beam of light and split it using a beam splitter. The light has to be coherent in order to preserve the phase information between the two beams. Then you take beam 1, called the illumination beam, and you allow it to interact with an object where the image information about the object is now contained in the beam. Then you have this other beam, called the reference beam, and what you do is you spatially overlap the reference beam with this object beam in a photographic material where the two beams can interfere with one another within this material and record a hologram of the image in this photographic plate. To read out the image, you bring in another beam called a reconstruction beam, and the holographic image that you recorded in the plate now actually scatters the waves in the reconstruction beam and allows you to reproduce the image. The key here is that the two beams used to record the hologram have to spatially overlap in the photographic material. This is an experiment that uses entangled photons for holographic imaging. You have a source that can produce entangled photons or photon pairs, and this is usually some type of nonlinear optical crystal. Then you send off your photon pair spatially separated, where one of the photons in the pair passes through an object and the other photon of the pair passes through free space. Now, the photon passing through the object contains information about the image of the object, and because the photons are entangled or correlated, the other photon has information about the object image as well. The pair of photons are then detected in highly sensitive cameras where the quantum spatial features of the light can be reconstructed and produce an image of the object. Here are a couple of images that were produced using this technique, a cat or maybe Schrodinger's cat, and down here producing some images of a couple of smiley faces. But there are several promising things about this technique. One is that it has a higher resolution than classical coherent imaging. Another is that it can allow imaging with wavelengths that were previously inaccessible, say, down into the IR. And third, it allows for imaging at lower photon levels, which is important for biological samples that can sometimes be sensitive to high photon fluxes. The next topic we'll talk about is how to get time resolution out of spectroscopy experiments. The timescales for dynamical processes in physics and chemistry can span orders and orders of magnitude in terms of how fast or how slow they are. For instance, processes like chemical reactions, like electrochemical processes and polymerization can happen on the second to millisecond time scale, while photochemical and photophysical processes happen faster, usually on a sub-microsecond time scale, and molecular vibrations and rotations happen on the sub-picosecond time scale and into the femtosecond regime. So I'm separating the techniques used to get time resolution in spectroscopy into fast frame rate spectroscopy, which can be used for processes happening on the second down to millisecond time scale, and pump probe spectroscopy, which is used typically for processes that are faster than microseconds. Now, fast transient spectroscopy can be used to study the electronic and structural properties of short-lived excited states, and some of the techniques used for this are transient absorption, transient emission, or time-resolved fluorescence, which we've seen, time-resolved resonant Raman, and 2D electronic spectroscopy, just to name a few. Chemical reactions are usually followed by slow transient spectroscopy, but no matter what timescales are involved, signals from these experiments can range from being in the UV out all the way into the shortwave infrared or even the infrared, and they can all be at very, very different photon flux levels. The idea behind a pump probe experiment is that you come in and excite a sample with a very short laser pulse. That's a pulse of light that can be turned on and off in a very short amount of time, and you create a transient concentration in your sample. Then you come in and look at this transient concentration at a time, delta t, after the pump pulse arrived, with another pulse called the probe pulse. Now, these pulses can be extremely short in time, from nanoseconds to picoseconds to femtoseconds, and people are now even producing attosecond pulses. That's 10 to the minus 18 seconds. How to probe this transient concentration depends on the time resolution the experiment needs or how small this delta t is. If delta t is on the order of nanoseconds to microseconds, then ICCDs can be used, and we'll describe how they work in the next slide. If delta t is smaller than nanoseconds, then optical delay stages are used to get time resolution. What they are is a pair of mirrors on a translation stage, such that you can vary the relative distance that the pump pulse and the probe pulse take to reach the sample. So for instance, by making the probe pulse travel a shorter distance to reach the sample, it will arrive before the pump pulse. But if you make it travel a longer distance to reach the sample, it will arrive after the pump pulse arrives, and that's how to get time resolution. Detectors in these experiments can be traditional CCDs, EMCCDs, SCMOS detectors, or sometimes even point detectors. Let's look at how ICCDs work. An ICCD is a camera with either a CCD or SCMOS type sensor that has several additional components in front of it. The first component is the photocathode, and the photocathode can be used to generate photoelectrons when exposed to light, but the key to the photocathode is that it's gateable on a nanosecond timescale. That means it can be made only to generate photoelectrons for very short, precise periods of time. Then you have a microchannel plate, which provides amplification of these photoelectrons to boost up the signal. The photoelectrons then strike a phosphor, which converts these photoelectrons into visible photons, which are detected on our 2D sensor. Again, this can either be CCD or SCMOS in design. CCD sensors are low repetition rate but have high dynamic range. SCMOS sensors provide fast spectral rates into the multi-kilohertz and also have high dynamic range. So because ICCDs can be used to control when our sensors are exposed to light with very high time resolution, they can be used for time-resolved spectroscopy. This is an experiment where an ICCD is used to monitor the reaction dynamics of a combustion mixture and where they use a laser to excite this mixture. What they do is they put a mixture of methane and air gas into a chamber and they pass an intense femtosecond laser through this mixture, which allows them to ignite the mixture and creates a flame. Over here you can see they're monitoring the time profile of the flame before ignition and then several time steps after ignition from 20 microseconds all the way out to 6 microseconds using the iStar ICCD. What also happens in this experiment is that when they excite the combustion mixture, they create a plasma, and they can use optical emission spectroscopy of the plasma to characterize the different components in the plasma mixture as a function of time after ignition. Here they're looking at the different concentrations of the OH and the CH radical as a function of the gate delay time after ignition. And this provides them information and insight about the mechanisms of the flame formation and of the combustion reaction. The last topic we'll talk about today is how to optimize throughput in a spectroscopy experiment. Throughout this presentation, we've been talking about different sensor designs and architectures and how these different designs and architectures can help us with the three challenges in spectroscopy that we initially identified. Here, we'll see how the CMOS sensor design can be used to maximize throughput in a spectroscopy experiment. Over here, I'm showing our conventional CCD, where a photoelectron is generated in a pixel and then travels down the other pixels to the readout register, where it's turned into a voltage. But this means that you can only read out one pixel at a time. In a CMOS sensor, each photodiode has its own readout circuitry built in, so you can read out whole lines simultaneously at a time, and this allows for much faster spectral readout rates on the order of thousands of spectra per second. It's also able to do this with very low read noise at any readout speed, so you can have high spectral acquisition rates at the same time preserve the dynamic range of your measurement because there's no need to increase the gain on the camera and the detector to overcome the read noise. Because of this setup is very well suited for chemical and elemental mapping where thousands of spectra might be required to create such a map. For our mapping experiment, we're going to look into creating an elemental map of a sample, and we'll do that using laser-induced breakdown spectroscopy. In a LIBS experiment, an intense nanosecond laser is focused on a sample where it is absorbed. This creates a crater in the sample where some of the sample is vaporized, and you can also have fragmentation, melting, sublimation, and atomization going on in the sample. Then, about 100 nanoseconds after excitation, you have the formation of a plasma, you get a shock wave, and the emission of several different types of light. By the time a microsecond passes after excitation, the sample has had a little time to cool and is now emitting photons that are element specific. And what I mean by that is if the sample is emitting a photon that's in the red, it might be coming from a nickel atom. A green photon might be coming from a chromium atom. That means that we can correlate the color of the emission with the elemental identity of an atom. And the emission intensities are related to the elemental concentration. And a couple of things to note about LIB spectrum in general is that they can be very spectrally dense. That is, they can have a lot of closely spaced spectral features. Some of these spectral features can be very strong, while others can be very, very weak. And these features can all happen over a broad spectral range. What are some of the things that we need to think about for this elemental mapping experiment using LIBS? Well, we need to measure microseconds after laser excitation in order to see the element-specific emission. That means we need time resolution. There also might be a wide range of concentration of the elements in our sample, so we need to measure both strong and weak spectral features at the same time. This means we need a detector with a high dynamic range. We talked about how LIB spectra can be spectrally dense or congested, so we would need a spectrograph that has high spectral resolution. And LIB spectral features can occur over a broad spectral range, and we'd like to be able to measure many wavelengths at the same time, so it'd be good to have a spectrograph that had a high spectral bandpass. And finally, since we're looking to create an elemental map and we need thousands of spectra in order to do this, we'd like a system with high throughput. On this slide, we're comparing spectra, one taken from one of our intensified cameras, the iStar CMOS in red, to another spectrum taken with an intensified camera with a CCD type sensor in blue. Now, while these spectra seem to have similar signal to noise ratios, the dynamic range on the ICCD is much lower, And we can see that these two main spectral features at 400 nanometers and 450 nanometers are being clipped on the ICCD, but the intensity of these peaks is captured on the I*S CMOS. And this is because more gain had to be used on the ICCD to account for the elevated read noise at these high readout rates. This effect can also be seen in this table over here, where we look at the read noise for a few different ICCD types at max readout rate, what type of gain is needed to overcome the noise floor in each of these detectors, and the resulting dynamic range that is possible on each of these platforms. And again, this is due to the unique SCMOS sensor design, where each pixel has its own electronics built in, which allows for rows of pixels to be read out at the same time. Here's an example of where LIBS is used to create maps of the concentrations of different elements in a sample, like we were talking about doing before. This is called kilohertz micro-LIBS imaging, and this work is courtesy of Vincent Moto-Ross at the ILM in Lyon, France. Here, the sample is placed on an XY translation stage so it can move around, and LIBS measurements are taken on the sample with the 10 micron spatial resolution. The light from the LIBS emission is sent to a Chimera 328, where it is dispersed and then detected with an I*S CMOS at a rate of 1,000 spectra per second. And this allows one to produce high-resolution images showing the concentration of different elements in a sample, like the ones here on the right. This image is showing the distribution of silicon in the sample. Here we're looking at the distribution of copper in the sample, and over here we're looking at the distribution of silver in the sample. And while these images are made from several thousands of LIBS measurements, they can take less than 3 hours to produce with this high throughput setup. That's all I wanted to talk about today. Thank you very much for your attention. This also wraps up our Fundamentals of Spectroscopy series, and I hope that you enjoyed these webinars and found them to be useful. I also encourage you to email me with any questions or comments that you might have at s.harrell@andor.com. Thanks again.